Okay, so hi, my name is Aurélie Suzanne. I'm a PhD student working for a collaboration between a university, Polytech Nantes, and a new company, Exmaniam, which is specialized in quality of service for telecommunication systems. Today, my topic will be about spanning events and how we can use them in streaming system, and in particular, how can we optimize the way we use them in streaming system with slicing techniques coming from the classical streaming systems. So let's start by explaining what I call a spanning event. Let's say you have a streaming system and you receive in this system a series of phone calls. In this normal system, you would have to choose if you want to keep the start point or the end point of the event as the time for the event. With spanning events, you don't need to make such a choice. For both the start point and end point, they will be kept, and all the points in between also. This means that you can have systems which adapt far better to the real world events. You don't need to truncate them. And at the end, you will have more accurate results. You have more accurate results because what we mostly do on streaming system is to have some aggregates depending on some windows. So here we have a series of spanning events, the phone calls we had just before, and we had some sliding windows. Those windows, they advance with the time by, let's say, I want to have all the information of what happened in the past 15 minutes, and I want to have this information every 10 minutes. What I want to do is, now that I have the windows, I want to have some information on them, on the form of aggregates. And for example, I want to know how many events were in the windows. So in this case, I would say that I had 5 events in each window. The problem is, how do I compute those results? And for this, let's move a bit backward to the point event stream. So now we have, again, some events, but those are point events. And we try to place them into some windows. A naive technique would be to say that I create a bucket for each of those windows, and then when an event arrives, I look into in which windows it was in, and I will insert it in every window. But for the green events, we can see that we need to duplicate this event and insert in several buckets for several windows. With the slicing technique, you don't need to make such thing. You don't need to duplicate the events. You create some slices, which are in fact some sub-windows which do not overlap each other, and you would insert the event in those slices. Then when you want to release the aggregate for the window, you just go and look into the slices and re-aggregate them together so that you can output the result for the windows. So those slices, they allow to have computation sharing among the windows. The green events are used only once. They also limit memory usage because you're in a slice, you won't keep all the events as the way you did with the buckets. You would keep only a pre-aggregated structure of the aggregate function you want to have. And the fact that you keep the result in a pre-aggregated form means that also when you want to release the aggregate for the window, you only have to use pre-aggregate results and not all the events, and hence you have much faster results. So now we can go back to the spanning event problem. And we quickly have a problem. If we look at only the second window and we look into point events, we can see that when adding all the slices from the second window together, we have a result of 3, which is actually the number of events we had in the window. When you want to do the exact same thing with the spanning events, you would end up with a result of 3 plus 3 plus 3, which is 9. But in fact, you had 5 events in this window. This is due to the fact that the spanning events, they can overlap several slices, and hence we will count them several times. So we need to find some ways to use the slicing techniques from the point event stream into the spanning event stream. So in this presentation, I will talk about the spanning event stream, and I will talk about the slicing technique coming from the point event stream towards the spanning event stream, and how we must adapt the techniques. And then I will show what the performance improvement we have from using slicing techniques in spanning event stream. So let's start with point event slicing. Basically, point event slicing starts with slice. And a slice is basically just an interval. And those intervals, they strictly follow each other. So we have no superposition because each time a slice ends, a new slice starts. And in those slices, we keep an internal structure. This internal structure is a result in a pre-computed form. And this pre-computed form depends on what aggregate function we have. For example, for a count, we would keep a count. And for a mean, we would keep a sum and a count. And then when we want to release the mean, we would use both of them. So now we can see also what's the function we will use on those slices. The first function we will use is the lift function. It will take an event, for example, an event arriving at 10:10 with a data of 3, and it would lift it into the internal structure. So if we take back the mean structure, we would have a sum of 3 and a count of 1. Then we have the combine function. This function, it would take 2 internal structures and combine it into a new one. So in this case, we would add the sums, 17 and 3, to output 20, and add also the counts, 1 and 4, to output a 5. Then, and the final function is the lower function. In this function, we would take the internal structure and lower it to have the final result of our aggregate. So now we would have the sum of 20 and the count of 5, and we would divide 20 by 5 to output a result of 4. So now that we have all those functions, we can see how we insert events in such systems and how we release windows. So the event insertion starts with lifting the event into an internal structure, and then we go and look into the slice array, and we extract the latest slice we created. We extract an internal structure, and we combine it with the internal structure we just created from the event. This creates a new internal structure, which we would then update into the slice array. When we want to release a window, we would go at the very beginning of the slice array with the oldest slices, and we would get the 2 first slices and combine them together. Then we would take this internal result, a structure result, and we would combine it with the next slice, and so on and so forth until we reach enough slices to have the same size than the window size. Finally, with this internal structure result, we would lower it so that we can release the final aggregate. So this is the story for the point event slices. And now we want to have the story for the spanning event slices. The first thing we need to consider is that we might have duplication among the slices of events. And for this, all the functions are not equal. The selective function, like max and min, they do not suffer from duplication because we would keep only one event. If this event is duplicated, I still have an accurate result. The cumulative function, like count, sum, and mean, and so on, they would have a first result and then they would accumulate data on top of that result. So if we have duplication, then we would have an accurate result. So let's start with those selective functions. Selective functions have no duplication problem. Hence, we can use a system very similar to the point event slices. So we have the events, we lift it again to the internal structure, but this time this event overlaps several slices. So we would need to go and find in the slices array all the slices which overlap with the event, and we would need to combine all their internal structure with the one from the event we just lifted, and then update all those slices. The release of the window would be exactly the same. When we have a cumulative aggregate function, we have this duplication problem. And our idea was to say that we can compensate for this problem by just duplicating the internal structure. So now each slice has 2 internal structures. The first internal structure contains all the events which end in the slice. The second internal structure contains all the events which end after the slice. This means that those events which are in the second internal structures, they will be seen afterwards, at least in the next slice. And this will have some implication we will see afterwards. So now how do we insert an event? This now looks quite a bit more complex. So let's look at it by pieces. When the event ends in the slice, I said that we would lift the event by only updating the first internal structure. So our event with the data 3 would be lifted into an internal structure composed of 2 internal structures, and we would update only the first part. Then when we want to combine the internal structures coming from the event with the one coming from the slice, we would first combine the two first internal structures together, and then we would keep the second internal structure of the slice. When the event ends after the slice, we now have to update the second part of the internal structure. And so we would do the exact same thing, but this time in the second part. And when we want to combine, we would take only the first internal structure from the slice and combine the two second internal structures from the event and from the slice. So we would continue this for all the slices which overlap the event. And then we have perfectly fine structure to keep those spanning events for cumulative aggregate function. Now to release a window, again, it's a bit more tricky because of this duplicate internal structure. So we would have a look at how we combine the two first slices together. We saw that the first internal structure keeps all the events which end in the slice. So we can combine them together to output the result, and the 17 would go with the 12 to output 29. For the second part, we said that the second part are all the events which end after the slice. So for the oldest slice, this means that all these events, they will be seen in the next slice, so we do not need to keep them. So we forget about the second part, internal structure, for the oldest slice, and we keep only the most recent one. And we would do that for all the combines, and making that at the end, when we combine all those slices together, we accumulate all the first internal structures of all the slices, and we keep only the last internal structure of the last slice. Then, to lower the result, we would do something quite similar to point events. We would add the sums and divide it by the counts. So now we can move on to some experiments.
We have something little than 3 minutes.
In the experiments, I first wanted to show what's happening when the event size grows bigger. We can see first that the naive technique buckets performs always worse than the new technique we had, the slices. And slices performs even better when the window size is getting bigger and when the event size is getting smaller. When we look at the overlapping, so how much the window overlap each other, we can see that for high overlaps, which are small steps, we reach a much higher throughput, much faster with slices and with buckets. This means that slices are really efficient at computation sharing among windows. And finally, for some telecommunication dataset we had a look at what are the throughput for varying window size, and we can see that slices always perform better than buckets by kind of the same size. So as a conclusion, we can say that streaming systems, they can be extended to use spanning events. We have a lot of spanning events nowadays, and it's quite nice to be able to use them in the way they are, which all on top of it provide more accurate results. And for using those systems, we can use the slicing technique from the point event stream. But we have some problems because spanning events, they introduce duplication among the slices. And for this, we need to create some specific structures to moderate this constraint for the aggregate function, which are sensible to it. At the end, even with the overhead we are creating to be able to use the spanning events and slicing technique together, we can see that we have better performances than, by using slicing techniques than by using naive technique as buckets. And that's the end of my presentation. Thanks a lot.
So thank you very much for your presentation and sticking to the time limits. We have some time for a few questions from the audience. So if you have a question, please unmute yourself and feel free to ask. Okay, while we are waiting, I guess, for some question, may I ask you if you are planning already some further development extension of your approach?
Yes, what we would like to do is to be able to have windows with multiple granularities, because right now in streaming system, what you often do is that you need a lot of information about the most recent data, but for all this data, you don't need to have a granularity of, let's say, 1 minute, because 1 day would be quite enough. So one of our ideas is to move this system to varying granularities and see how we can use it.
Do you have any specific application domain in mind? I see you are using telecommunications as an example.
Yeah, yes, but because I'm also working for a company, and my company is specialized in telecommunication systems, so it's kind of easier to know what the data sets are and to have some real applications when.
Mhm. Do you know what maybe other application areas, perhaps, where you can find even some data sets, maybe?
Finding data sets is not easy because spanning events are not so used in streaming systems right now, but we could think of basically anything which has duration, so maybe weather data or network data, or all the IoT systems also maybe.
Mhm.